Welcome back to Basic Mathematics. Relations and functions. Today in this video, we are going to understand the basics of functions and relations in mathematics. Functions and relations. Function is a special group of relation. Function is very important in mathematics and equally useful in science, engineering and other area of calculations. There are variety of functions such as algebraic function, trigonometric function, exponential functions, etc. Before we define a function, we have to go to the relations in mathematics. Relations. In mathematics, relation means relation between two variables or between two parameters or between an object and a number. Consider the relationship between the weight of some boys and their ages as shown here. This type of information represents a relation between two sets of data. This information in table can be given in a set of ordered pairs: 11, 30, 12, 31, 13, 33, 14, 35, 15, 38. An age of 11 years would correspond to a weight of 30 kilograms. An age of 15 years would correspond to a weight of 38 kilograms, and so on. The set of all first elements of the ordered pair is age, and the set of all second elements is weight. The set of all first elements of the ordered pair is independent variable and is called the domain of the relation. The set of all second elements is dependent variable and is called the range. Here the domain equals 11, 12, 13, 14, 15, and the range equals 30, 31, 33, 35, 38. Note: 11, 30, and 30, 11 are not the same. Mapping of relations. The set of the ordered pair x, y is mapped here, showing independent variable corresponds to dependent variable, which define the relationship. Independent variable or x value or element of the domain are 11, 12, 13, 14, 15. Corresponds to dependent variable or y value or the element of the range 30, 31, 33, 35, 38. Mapping of relations. The set of the ordered pair x, y is displayed in Cartesian plane. (11, 30, 12, 31, 13, 33, 14, 35, 1538. A relation is any subset of the Cartesian plane and can be represented by a set of ordered pairs x, y, element of set of real number times element of set of real number, where the Cartesian product element of set of real number times element of set of real number equals square of element of set of real number represents the region covered by the whole of the Cartesian plane. Types of relations. Note: relations fall into one of four categories. These are 1. One-to-one relations, 1x to 1y. 2. One-to-many relation, 1x to many y. 3. Many-to-one relation, many x to 1y. 4. Many-to-many relations, many x to many y. One-to-one relations, 1x to 1y. For any one value of x, there will be only one corresponding value of y. To explain it further, we draw a function of x or y versus x on Cartesian plane or graph. For any value of the x1 on the curve will have only one value of y, y1. This is one-to-one relations between x and y. One-to-many relations, 1x to many y. There is at least one value of x, for which there exists more than one corresponding value of y. To explain it further, we draw a function of x or y versus x on Cartesian plane or graph. For any value of the x1 on the curve will have two values of y, y1 and y2. This is one-to-many relations between x and y. Many-to-one relations, many x to one y. There are at least two different values of x that will correspond to only one value of y. To explain it further, we draw a function of x or y versus x on Cartesian plane or graph. For three values of the x, x1, x2 and x3 on the curve will have same values of y, y1. This represents is many-to-one relations between x and y. Many-to-many relations, many x to many y. There are at least two different values of x that will correspond to at least two different values of y. To explain it further, we draw a function of x or y versus x on Cartesian plane or graph. It is an ellipse. Here for three values of the x, x1, x2 and x3 on the curve will have two values of y for each value of x, in terms of 0, y1, y2, y3, and makes many ordered pair for same x. This represents is many-to-one relations between x and y. Functions. Definitions. There is a special group of relations which are known as functions. This means that every set of ordered pairs is a relation, but every relation is not a function. Functions then make up a subset of all relations. Definitions of a function. A function is defined as a relation that is either one-to-one relation or many-to-one relation. That is, a function is a relation for which no ordered pairs have the same first element, there are two ways to determine if a relation is a function. Method 1. Algebraic approach. Method 2. Vertical line test. Algebraic approach. To determine if a relation is a function, we explain it with an example. Let a relation is y cubed minus x equals 5. We rewrite that y equals cube root of 5 plus x. Then for any given value of x, say x equals a, we have that y equals cube root of 5 plus a, which will only ever produce one unique y value. Therefore, the relation y cubed minus x equals 5 is a function. In fact, it is a one-to-one function. Algebraic approach. To determine if a relation is a function, we explain it with the example of relation y squared plus x equals 4. From y squared plus x equals 4, we have that y squared equals 4 minus x, or y equals plus or minus squared root of 4 minus x. Then, for any given value of x, say x equals a, where a less than or equal to 4, we have that y equals plus minus squared root of 4 minus x, meaning that we have two different y values, y1 equals squared root of 4 minus a, and y2 equals minus squared root of 4 minus a, for the same x value. Therefore, this relation is not a function as it is a one-to-many relation. Vertical line test. To determine if a relation is a function. Step 1. Draw the sketch of the relation on x, y graph. Step 2. Any vertical line within domain ever cut. At one place the graph, the relation is a function. Note it on the diagram of a function, which shows clearly only one cut. To compare, we have another diagram where a vertical line makes multi-cuts. 3 cuts means 3 y values for one value of x. Hence it is not a function. Functions and relations. For boys, A, B, C and D appear in a test which has 5 questions. Depending on their performance, they get marks from 0 to 5. The domain is the set of names A, B, C, D. The codomain is set of marks 0, 1, 2, 3, 4, 5. Marks are related as A2, B3, C4, D5. The mark of each boy is shown here in the arrow diagram on the right. By choosing any one name from the set of names, we can find the mark that relates to it, any relationship which takes one element of one set and assigns to it one and only one element of a second set, is said to be a function. Here we show you the mapping of marks as A to 2, B to 3, C to 4, and D to 5. Each element of the first set, or domain, is mapped onto its image in the second set, or codomain. The set of all images 2, 3, 4, 5 will be a subset of the codomain and is called the range 2, 3, 4, 5. By choosing any one name from the set of names, we can find the mark that relates to it. This is said to be an one-to-one function. In second case, A and B gets 3 marks, and C and D gets 5 marks. This is said to be a many-to-one function, and the range is 3, 5. Third case is one-to-many relation, and fourth case is many-to-many relations. Both of these cases are not functions. In our case, one-to-many means boy A getting marks 2 and 3, boy D getting marks 4 and 5, which is not possible, as one boy cannot get 2 marks in a test. However, the same marks can be given to many boys, or many-to-one. One-to-many is not a function, and many-to-one is a function. Suppose a function is such that it doubles any element x of the domain set X, and to give the corresponding element of the range 2 images to 4, 3 images to 6. This function would be read as f is a function under which each element x has an image 2x, or function of x equals 2x. As this function would map the number 2 onto its image, the number 4. We write this fact as f is a function under which 2 has an image of 4, or as f 2 equals 4. Other letters such as g or h may be used in place of f if we wish to distinguish between functions. Function as a machine. Can you think of functions as machines? A box of numbers. The domain is put into the machine. The machine then alters each number according to some rule, and outputs the new numbers into a second box. The range. The domain is 1, 2, 3, 4. Function machine. F is a function under which each element x has an image x minus 3. This machine subtracts 3 from each number. Finally, the range is -2, -1, 0, 1. Composite function. It means we are taking 2 or more functions together. Consider the functions f(x) equals 2x minus 1 and g(x) equals x squared. Using the machine analogy, suppose we input the numbers 1, 2, 4, 6 into machine f, and then take the output from this machine and put it into machine g. Now watch the process. This combined function, or composite function, is written as g(f)(x). Notice that the function f is performed first, and so is written nearer to the variable x. The set 1, 2, 4, 6 is the domain for the composite function, and 1, 9, 49, 121 is the range. To understand better, we take an example. If a function f x equals 2x and another function g x equals x squared minus 1, we find the range of the functions g f x for the domain -2, -1, 0, 1, 2. It is demonstrated below using the machine analogy. We get the range as -1, 3, 15. The inverse function. The inverse of a function. Consider a function f, which maps each element x of the domain x onto its image, element y in the set of range y. That is, f is a function under which each element x has an image y, where x element of x and y is element of y. Can we find the inverse function, written as f inverse, that has domain y and range x, which maps y back to x? That is, f is inverse function under which each element y has an image x. First, recall the definition of a function. Any one-to-one or many-to-one relationship is a function. However, if we attempted to find the inverse of a many-to-one function, we would obtain a one-to-many relationship, which is not a function. Thus, only a one-to-one function can have an inverse function. The following diagrams illustrate these points. We take a domain x of elements, say x1, x2, x3, and a function fx. To convert it to one-to-one, element y1, y2, y3 of the range y. Then we take output range as domain y of element y1, y2, y3, and use inverse function to get the element x1, x2, x3 of the set of the range as x. F is a one-to-one function. F inverse is one-to-one, and so it is a function. The following diagrams illustrate another points. For many-to-one function g x of domain U and range V, we take a domain U of elements, say U1, U2, U, and a function g x. To convert it to the range of element V1, V2. Then we take output range as domain V of elements V1, V2, and use inverse function g to get the element U1, U2, U3 of codomain. G is many-to-one function, and G inverse is one-to-many relation, and so it is not a function. In mathematics, the inverse function of a function f, also called inverse of f, is a function that undoes the operation of function f, and inverse of a function exist if and only if function f is bijective. A bijection is a relation between two sets, such that each element of either set domain is paired exactly one element of other set codomain. A bijection, or bijective function, or one-to-one relation, between two mathematical sets is a function. To find the inverse of one-to-one function, we write the separate operations of the function as a flow chart. We then reverse the flow chart, writing the inverse of each operation. We take an example to find the inverse of a function f(x) equals 2x plus 3. Inverse function. First, we write the function as a flow chart with input x and output 2x plus 3. Input x passed through the multiplication of 2 to become as 2 times x, and then added 3 to get the output 2x plus 3. Now reverse the flow chart and write the inverse of each operation. So plus 3 turns to minus 3 and multiplied by 2 becomes divided by 2 with input x. This will now output the inverse function turns to x minus 3. In next operation it will be whole divided by 2, leading it to x minus 3 whole divided by 2. So the inverse function is or function inverse of x mapped to x minus 3 whole divided by 2. You may check with a value of x equals 3 or function of element 3 lead to range of 9, and function inverse of element 9 lead to range of 3. Algebra of functions, basic operations, and composite functions. For two real functions, function f of domain df, under which df mapped to set of real number, or y equals f(x), defined over domains df, and function g of domain dg under which dg mapped to the set of real number, or y equals g(x), defined over domains dg. Have you noticed? The arrow to r is symbolize mapped to set of real number. Now we will follow the rules of algebra, which are applicable functions. Basic addition operations. The rule of algebra apply. Rule: sum of functions f and function g of element x equals function f of x plus function g of x and domain d of function f plus g equals domain of combined function of f plus g is intersection of domains of function f and function g. Example for function f from 0 to infinity mapped to set of real number as function f x equals square root of x, and function g mapped to set of real number as function g x equals x. We have domain of combined function of f plus g equals domain of f intersection domain of g equals from 0 to infinity. Therefore total function f plus g of x equals square root of x plus x. Basic subtraction operations. The rule of algebra apply. Rule: subtraction of functions f from function g of element x equals function f x minus function g x, and domain df minus g equals domain of function of f minus g is intersection of domains of function f and function g. Example: for function f from 0 to infinity mapped to set of real number as function f x equals square root of x, and function g are mapped to set of real number as function g x equals x. We have domain of combined function of f minus g equals domain of f intersection domain of g equals from 0 to infinity. Therefore combined function f minus g of element x equals square root of x minus x. Basic operations of multiplication. Rule. For two real functions, function f of domain df under which df mapped to set of real number or y equals f, x, defined over domains df. And function g of domain dg under which dg mapped to set of real number or y equals g, x, defined over domains dg. The multiplication rule apply as f times g of element x equals f, x, times g, x, and domain df times g equals domain of function of f multiplying g is intersection of domains of function f and function g. Example: if f, x, equals 2 divided by x minus 1, where x is element of set of real numbers where x is greater than 1 and g, x, equals 1 minus x squared. Therefore, f times g, x, equals 2 divided by x minus 1 times 1 minus x squared. Or, f g, x, equals minus 2 times x plus 1. Basic operations of division. Rule. For two real functions, function f of domain df under which df mapped to set of real number, or y equals f, x, defined over domains df, and function g of domain dg, y equals g, x, defined over domains dg. The division rule apply as f divided by g of element x equals f, x, divided by g, x, when g, x, not equals 0. Example: if f, x, equals x squared and g, x, equals x plus 1. Therefore, f divided by g, x, equals x squared divided by x plus 1. Basic algebraic properties. For real numbers, a, b, and c are element of set of real numbers. Then a plus b are also element of set of real numbers and a times b element of set of real numbers. Commutative rule applies. A plus b equals b plus a under addition. And a times b equals b times a under multiplication. Associative rule applies. A plus b plus c equals a plus b plus c under addition. And a times b times c equals a times b times c under multiplication. Basic algebraic properties for real numbers. A, b, and c are element of set of real numbers. Then a plus b are also element of set of real numbers and a times b element of set of real numbers. Existence of the identity. A plus 0 equals 0 plus a equals a, it is 0 under addition. And a times 1 equals 1 times a equals a. And it is 1 under multiplication. Inverse element. Minus a. A plus, minus a, equals 0. Equals minus a, plus a under addition. And it is 1 divided by a. 1 divided by a times a equals 1 equals a times 1 divided by a. Under multiplication. The identity function. We define the identity function, I, as function I, x, equals x. If an identity function, I, exists, then it must have the property that for any given function f, the composite function f and function I equals the composite function I and function f equals function f, or the composite function f o function I of element variable x equals the composite function I and function f x equals function f x. Inverse function. Using an analogy to the real number system, the concept of an inverse requires that given some function f, there exists an inverse function, f inverse, such that the composite function f and inverse function f equals function I equals the composite inverse function f and function or the composite function f and inverse function f of variable x equals the composite inverse function f and function of variable x. We summarize our findings. For the inverse function, f to the power of -1, we read it as f inverse 2 exists, then 1. Function f must be an 1-to-1 function. 2. The domain of function f is equal to the range of function f inverse. That is d f equals r f inverse. 2. The range of function f is equal to the domain of function f inverse, that is r f equals d f inverse. 3. Function f of f inverse 1 of variable x equals function f inverse -1 of function f x. How do we find the inverse function? A guideline for determining the inverse function. Step 1. Check that the function under investigation is a 1-to-1 function. This may be done by using a sketch of the function. Step 2. Use the expression function f of function f inverse of variable x equals x to solve for function f inverse of variable x. Step 3. Use the fact that domain D of function f inverse equals range R of function f and domain D of function equals range R of function f inverse to complete the problem. Example. Find the inverse of the function fx. Map to 4x plus 3, where x is the element of the set of real number. Check if the function is a 1-to-1 function from the graph or from observation. As function is an equation of straight line, it is clear that function f x is a 1-to-1 function. Making use of the result that function f of function f inverse x equals x to solve for function f inverse x. Or as function f x for x plus 3, replacing x by function f inverse x. We have, then function f inverse x equals for function f inverse x plus 3 equals x, or for function f inverse x equals x minus 3. Or function f inverse x equals 1/4 times x minus 3, function f inverse x equals 1/4 times x minus 3. There is a second method that we can use to find the inverse of a function. The steps required are: Step 1. Let y denote the expression function f of x. Step 2. Interchange the variables x and y. Step 3. Solve for y. Step 4. The expression in step 3 gives the inverse function f inverse of x. We work through an example using this method. Example, find the inverse function f inverse of f x 3x plus 4 where x set membership symbol. Step 1. Let y denote the expression function f x. Let y equals function f x, giving y equals 3x plus 4. Next, step 2. Interchange the variables x and y. That is, x equals 3y plus 4. Step 3. Solve for y, or 3y equals x minus 4, or y equals 1/3 x minus 4. Step 4. The expression in step 3 gives the inverse function f inverse of x. Therefore, the function f inverse of x equals 1/3 x minus 4. Thank you for watching this video on relations and functions. For watching our other videos of past and future, you may please Subscribe the channel.